students. As you may remember that till the last class we were discussing about different type of steel springs, and in the same topic, under the same topic of steel springs, we discussed about construction and working of leaf springs, as well as the construction and working of coil springs, along with their load estimation, load calculation, deflection, stiffness calculation. So today we are going to solve a couple of problems based on these leaf spring and the coil springs. Hope you will understand some of it and try to solve more problems based on the same topic. Okay, moving forward. See, this is the first question. Based on leaf springs, you can see that a vehicle spring of elliptic type has a leaves. Elliptic type means elliptic leaf spring, semi-elliptic, fully elliptic, quarter elliptic. These are the different types of leaf springs we discussed. So this is one of the kind of leaf springs. What I want to say is, okay, so this is one kind of leaf spring, elliptic leaf spring here. Okay, it has 75 mm width. You can say if I try to draw the blade of a leaf spring, it is kind of like this. This is the blade of the leaf spring. So the width of this blade is 75 mm, and the thickness, if I try to draw it in a 3D case, like in this case, the thickness of this blade is 10 mm. Okay, and effective length of this leaf spring is 900 mm. Effective length means the distance between the two spring eyes. We discussed there are two spring eyes, one is connected with the shackle and another one is connected with the help of bushes. Fine, so the distance between those two shackle eyes or spring eyes is 0.9 or meter or 900 mm. Now if it is assumed that the stress is not required to exceed this value 220,725 kilopascal when the spring is loaded with a weight of 4905 Newton. Suppose a 4905 Newton of weight is applied over the axle, so this load is transmitted to the spring. So in this condition, stress should not exceed this value. Okay, so we need to estimate for this to achieve this particular condition how many number of leaves are required in the leaf spring. Now if you assume that initially it is curved, initially the leaf spring is curved, and due to the application of the load the spring will try to flatten out. So it has been asked that if the spring is flat under the load, what is the initial radius of curvature? Let's say what is the radius of curvature for the spring initially before the load has been applied to this spring. So I hope the question is clear to all of us. Okay, now three things. First, you need to understand what is the physics of this problem. So to understand the physics of this problem, we need to draw the diagram. So randomly I have tried to draw a elliptic leaf spring, okay, having some basic dimensions or basic basic parameters given in the problem, and then I'll try to list out what are the variables given to me in this problem. So sigma and the bending stress, the maximum permissible bending stress is given to me, okay, 220,725. B, I'm assuming B is the width of the blade, so that is 75 mm, thickness of the blade 10 mm, and E, modulus of elasticity, is given to me. It is 196.2 into 10 to the power 6 kilopascal. Okay, now we have, if you remember, we have derived some relations for the leaf springs for the lecture of 1st April. If you try to open the file of 1st April, you will see some important relations for the leaf springs. So one of the important relation for the leaf spring was that permissible bending stress is given by this expression 3/2 WL divided by BT square into N. N is the number of blades. Okay, so all of these values, let's say the W is given to me, L is given to me, the width and thickness is given to me, and I need to calculate number of leaves for the given value of sigma, and the given value of sigma, you're clear that it is 220,725 kilopascal. So upon substituting these values, if I substitute this value, what I need to do is I will take this n to this side and I will put the sigma over here. So we'll replace n and sigma. Okay, we will swap the values of n and sigma in this expression, and then we can write another expression that n will be equal to 3/2 WL bt square by bt square sigma. Okay, so now what we will do here is we have substituted the value of all the given parameters, and then we have found that n to be approximately 3.99. So for having 3.99 blades, we will approximate it to 4. There should be 4 leaf springs blades available in this case. Let's say if the answer has came out to be 3.2 or 3.1 or 3.3, so in that case also we will approximate the number of leaf springs to the value of 4, not to the value of 3, because we will always try to design the leaf spring for maximum conditions or for factor of safety or for extra clearance. So we will never round down. In this case we will always round up. Okay, now secondly, first part which was asked in the question is to calculate the number of blades. So this is the number of blades for satisfying the given condition. Now it has been asked that for the same condition what should be the deflection in the leaf spring, and in the same lecture, April 1, we have derived the expression for the deflection of leaf springs. You can see the file again. So the deflection expression came out to be this expression: delta is equals to 3WL cube by 8E n bt cube. Okay, W applied load, L is the effective length, 8, E is modulus of elasticity, N is number of number of blades, B is the width, and T is the thickness. So all of these quantities are given in the problem. So if I substitute all of them over here, I can get delta to be near about 0.022 meter. Why meter? Because I have assumed I have taken all the dimensions of length in meters. So the answer has came in meters. And if I want to calculate this in millimeters, so the deflection of the leaf spring is 22 millimeter for the same case. Okay. Now the third thing was also calculated before. If under the load, if the spring gets flattened out, so what was the radius of curvature of the spring initially before the application of the load? And we have also derived this relation that delta is equals to L square by 8R. Okay, so if I substitute the value, I would need to calculate the value of this capital R, that is the radius of curvature. So for the capital R will be equal to L square by 8 delta. So if I substitute the value of these things over here, I will get initial radius of curvature was around 4.6 meter for the same case. Hope you understood. Let us just revise what was asked and what we did. Okay, initially some dimensions, some design parameters were given to us, some loading conditions were given to us, and we need to calculate some other parameters required for designing and operating conditions. So we needed to calculate the number of leaves and the deflection for satisfying this particular condition. For satisfying this particular condition, that is that if I don't want to exceed the bending stress to be this value and under this much amount of load. So we calculate number of leaves to be 4 and deflection to be near about 22 millimeters, and then it has been asked if the spring gets flat under the load, what was the initial radius of curvature for the elliptical leaf springs. So that for calculating this, we have used this expression delta is equals to L square by 8R. So we have calculated initial radius of curvature to be 4.6 meters. Hope you understood this. So this was about a problem on leaf spring. Let's see what type of questions can be asked in case of a coil spring. Okay, this is one question based on coil spring. We can see a typical coil spring has 10 effective turns. Okay, you can very much understand this word is, let's say a coil spring has different number of coils, different number of turns. So it can be said that for this particular case there are 10 turns, 10 coils in this coil spring, and each turn having mean diameter to be 125 millimeter. Mean diameter, that means the mean diameter of the coil, okay, not the wire. Okay, and the wire diameter is 15 mm. Okay, so we have discussed this in lecture number I think the lecture of 9th April. So if you open the file of 9th April, you will see the calculations of leaf spring, and then there I have told you that the wires with which the coil springs are made, their cross section is circular. So for that circular cross section wire, the diameter is 15 mm. Okay, now it has been given in the problem that the spring is designed to calculate a maximum load of this much. Okay, so that we should every time we should take care that the load on the coil spring should not exceed this value 3531.6 Newton. Okay, so for this much amount of maximum load, it wants us to ask it is asking us to calculate shear stress and the deflection for this much amount of load and for these designing conditions. Okay, so this is the part one of this question. There is a second part also. We'll discuss the second part later on. First, let us try to discuss the first part. So let's say if this is a coil spring and this much amount of load is acting on this coil spring, this is 3531.6 Newton, and the given parameters are like the number of turns are given 10, diameter, the effective diameter of the coil is given to be 125 millimeter, and the diameter of the wire is 15 millimeter. So we know that coil springs also follow the, you can say, twisting or the torsion equations, and the torsion equation, one of the relation is T by J is equals to tau by R. T is the applied torque, so applied torque will be due to this load, by J. J is the polar moment of inertia, tau is the permissible shear stress, and R is the radius of the wire. Okay, so if we simplify, we have done this derivation in that lecture of 9th April. You can refer the same material, same content. Okay, so upon simplifying, we got that permissible shear stress for this condition should be given by this expression 16 W into capital R divided by pi d cube, where this capital R is the radius of the coil, effective radius of the coil, W is the applied load, and D is the diameter of the wire. So all of these values are given to us in the problem. Simply just substituting these values over here, we will calculate the permissible shear stress which is asked in over here. Shear stress, the permissible shear stress will be this value 33079.46 kilopascal. Now the second part is, it is asking us to calculate the deflection also, and in the same content we have derived this expression for deflection of the coil spring, which is given by delta is equals to 64 WR cube N by GD to the power 4. Now G is the modulus of rigidity for the given material. Okay, so if I substitute all these values, these are also given to us in the question. So on substituting, we will get the delta, the deflection for the spring for the given situation, for the given conditions is 0.148 meters or 148.1 millimeters. So these are the first two things which are asked in the question to calculate the shear stress and deflection for this loading condition. Okay, tau is this, shear stress is this, and deflection is this. Now we need to calculate the second part also. Let's see what does this part says. It is asking me that if the maximum shear stress, now the maximum shear stress is given for the given material. Okay, so maximum allowable shear stress is given to us, that is 637,650 kilopascal. Then it is asking me what should be the possible clearance of the spring. Now what do you understand by the term clearance of the spring? See, initially we have assumed that this much amount of load I want to apply on the spring, I don't want to exceed this much amount of load. Okay, so for this much amount of load we have calculated delta to be near about 148 millimeters, but we know that the shear stress, maximum shear stress allowable is this much, so delta can be greater than this value. Why greater? Because for this much amount of load, tau is 330.33079, and here the maximum shear stress is much greater than this value, so delta can also be greater than this value. So we will say for this much amount of shear stress, how much is the maximum value of the deflection. So that somehow if I can calculate the maximum deflection for this shear stress, and we had calculated the deflection for the maximum loading condition delta, we can say upon this maximum loading condition, that delta and what could be the maximum possible of delta, the difference between those two delta will be the clearance of the spring. Okay, so let us try to understand this thing. Now see, we have been given that tau max for the given material of the spring is this much value, 637,650 kilopascal, and you know from the torsion equation itself we have this relation G theta by L is equals to tau max by R. And also we know that in case of springs, delta is equals to theta into R. Okay, you can refer the same content of 9th April. So if I substitute the value of this delta, if I substitute the value of this theta as delta by r over here, so theta will be delta by r. Okay, so I can do it like this, and then we will see what we will see, that g delta max by r by l is equals to tau max by r. Fine. So from here I can calculate delta max to be tau max l r g r small r, tau max l capital R divided by g into small r. Or I can say is delta max will be tau max. Now what is this L? L is the length of the wire of the spring. Now length of the wire of the spring, you very well understand, it could be written as circumference of the turns, and you know the circumference of the turn are uh, circumference of the turn can be calculated as L equal to 2 pi capital Rn. Okay, so what I have done over here is, so this L will be equal to 2 pi capital R into n. Okay, so this L equal to 2 pi capital Rn should be substituted over here. Okay, and this R is already there, so 2 pi R square, and there should be an n also. If I substitute the value of this L over here, 2 pi Rn, so this expression will become tau max equal to 2 pi R square n divided by g into small r. So small r can also be written as g into small d by 2. Alright, hope it is clear. So upon substituting these values, you can check the calculation. I think if I include n also, then also the answer will come in this way. There should be n. I should multiply n is 10 given in the problem. So here I have substituted this n, okay, 10. So upon using this calculation, upon substituting using this calculation, I have seen that delta max is this value 283.66 millimeters. And you know, for the maximum loading condition of load of some 3000 newtons, we calculated delta to be around 148.1 millimeter. So maximum allowable deflection is 148.1 mm, but since the material can bear a maximum deflection of up to 283.6 millimeter, so in the maximum deflection condition also there will be a clearance of about 135.5 millimeter. How I am calculating? It is the difference between the maximum deflection and the maximum allowable deflection. Okay, so that will be the clearance of this spring. Okay, so hope this problem is clear to you. I will recommend you to solve some more problems based on these springs, leaf springs and coil springs. You can make use of any books which are available to you in which the spring topic is available. Some of the suggestions are like you can use the books which is based on the designing of the springs also, so you can refer those books, or otherwise I will share some PDF with you for the problem solving. Okay, now in the next lecture we will try to discuss about the torsion springs, design of torsion springs, and if possible some numericals based on the torsion springs. Thank you. Have a nice day.